We begin this section with a little story. Our story begins a long time ago, back in the early 1960s, when NMR was a new technique and researchers were reporting newly measured spectra on routine molecules, since they had never been measured using this technique before. In the wilds of South Georgia, we come to the lab of a young and rather dashing young chemist about to run their new NMR instrument for the first time. I just ran methanol on our new 60 megahertz electromagnet NMR, and I got a value of 60 megahertz exactly for the methyl group in there. I'm going to write that up and get a publication. Meanwhile, somewhere else in the state of Georgia, yeah, I had a graduate student run it on our new 250 megahertz superconducting magnet, and we got a value for the methyl group of methanol at 250 megahertz. So I guess that must be the right value. So the NMR community finds itself in a bit of a pickle. After all, two different researchers have measured the same molecule and found a resonant frequency that are quite different from each other. I know, it's shocking. But wait, the situation gets even worse. Meanwhile, in the wilds of South Georgia, time has passed, and our researcher, still dashing but now aging gracefully, has been working on their new 400 megahertz superconducting NMR. I've just run methanol on our new instrument, and now the methyl group has a resonance of 400 megahertz. So I'm going to update that value and get a new publication. Meanwhile, yeah, I just had my postdoc run that methanol in this 900 megahertz bad boy, and we got the methyl group out there at 900 megahertz now. So there you go. All kidding aside, this is a major issue in NMR spectroscopy, and is unique to NMR. It's not one that you see in many of the other forms of spectroscopy. For example, the carbonyl stretching frequency of acetone when measured in IR spectroscopy is the same whether it was measured, 30 years ago or yesterday on an old instrument or on a brand new instrument, mainly because that frequency depends solely on the strength of the bond. But in NMR spectroscopy, our frequencies actually have two dependencies. One of them is given by nature, the magneto-gyric ratio, but the other one is B naught, the big honkin' magnetic field. And since that one costs money, you have, various size magnetic fields attached to these instruments, some stronger than others. That means everybody with a different instrument measures a different frequency for all of our chemical shifts, even if we're running exactly the same molecule. This is why we need a standardized scale for NMR spectra, and the one we now use is called the PPM scale. If you've ever looked at the x-axis of a NMR spectrum, whether it's proton or carbon or any other nucleus, that axis is frequency, but it's not directly frequency. It's a relative frequency. It's referred to as ppm, parts per million. I have had more than one chemist in my career tell me, ppm, really? I did not know NMR was that sensitive, could measure concentrations that low. And I just smile and sigh and go on to explain that no, it is not part per million concentration, it's part per million in the resident magnetic field. And so back in the 50s and 60s, there was recognized a strong need to standardize NMR spectra. And that led to a search for a chemical compound that we could all agree would be the standard. And so the search was on for a reference standard to be used in NMR spectroscopy. And it was decided you needed to have it meet, whatever you chose had to meet a number of different criteria. For example, the signal that you're going to use as a reference standard, the chemical compound you might use as a reference standard, You would like it to not be in the middle of an NMR spectrum. You don't really want it popping up right in the middle of your aromatic region, for example. So you'd like to find a chemical compound that would either be unusually upfield or downfield. You would want it to dissolve in almost all of the classic organic solvents you would use for NMR. You really don't want to have a different reference standard for each and every solvent you might use. You don't want it to be terribly reactive. It would be kind of depressing if you had your sample that you had just synthesized after a 20-step synthesis. You added a little bit of the reference standard and suddenly your sample exploded because of a highly exothermic chemical reaction that occurred. So you want one that's going to just kind of sit there and not react with anybody. You want it to also produce a strong signal, so you don't need to use very much of this at all. So it ought to have quite a few equivalent protons or carbons in it. And especially for places like Georgia Southern, we want it to be cheap. We don't want to have to spend, lots and lots of money for a reference standard or something. Given all those criteria, the chemical compound called TMS, tetramethylsilane, is the one that was chosen and is currently the reference standard used for both proton and carbon spectra. And it is almost always the most upfield signal in an NMR spectrum, and in both proton and carbon we set TMS to be 0 ppm, and we essentially measure every other signal, every other chemical shift in our sample relative to TMS. And now we'll look at a little bit of the quantitative details on how that works. All right, we're going to follow up now with some quantitative details. I'm going to go back to methanol. This was the compound I was kind of fancifully talking about as something measured in various NMR instruments, some with weaker magnetic fields, some with stronger magnetic fields. Now, what I want to convey is on an old instrument, and we used to have one of these that operated at 60 megahertz. Okay? We would have said before the standard TMS was used, we would have said something like this, that the CH3, the methyl group of methanol, was measured at 60 million hertz, 60 megahertz. That was its frequency. Using TMS, this would be like the old way of doing it. The new way of doing it, using the TMS standard, would be to say that the methyl group here in methanol is 210 hertz downfield from TMS. Okay? Now come back to that point in just a moment. On our new instrument at 400 megahertz, under the old system, we would have said the methyl group was measured at a frequency of 400 million hertz. Under the new system reference to TMS, we would say that the methyl group is, let me make sure I get my number here correct, 1400 hertz downfield from TMS. Now, that doesn't seem like much of an improvement, but now look at this. 210 hertz divided by 60 megahertz times 1 million. If you were to do that calculation, you would come out with a number 3.5. 3.5 parts per million. If you do exactly the same calculation, but now on the new instrument, you would say 1,400 hertz from TMS divided by the base frequency of our instrument, which in the protons is 400 megahertz, times 1 million. And you would come out with 3.5 parts per million. That is the reference standard and how it gets used. And that is how NMR spectroscopists with old, smaller magnets, mid-sized magnets, or even the newer, most powerful magnets available, can report chemical shifts of any of the compounds we study and report the exact same value. That's because we don't report absolute frequencies, we report parts per million frequencies related to the base frequencies of the instruments we use. Let's consider this now. On our protons, and we've seen plenty of proton spectra now, we will notice that the range of peaks tends to fall most commonly in the range 0 to 12 ppm. I want to look at exactly what frequencies that represents. And to do that, kind of what we talked about a moment ago, remember on our particular instrument, on our 400 megahertz instrument, 1 ppm is 400 hertz. In other words, 400 hertz difference in frequency per ppm. So for the protons on our particular instrument, the protons range over 12 ppm. 1 ppm is 400 hertz. That means then that on our instrument, our proton spectra range over 4,800 hertz. Now, to put that in perspective and to kind of tie in with what we've talked about previously in magnetic nuclei and the frequency that they undergo their various transitions, imagine the full proton spectrum for a moment. There would be 0, there would be 6, there would be 12 ppm. Pretend for a moment that that is exactly 400 megahertz, right there in the dead center. That would imply then that the protons on our particular instrument are found at 400 million hertz plus or minus 2,400 hertz. Okay? In other words, it could be a total of 4,800 hertz across here, 2,400 downfield from the very center, or 2,400 hertz upfield from the center. In other words, on our instrument, that gives a range of 399,997,600 to 400,000,2,400 hertz. That's the range of protons on our particular instrument. This 400 megahertz, this 400 million, that is the influence of the magnetogyric ratio. That is the influence of the big magnetic field. This is the influence of the electron clouds, the chemical shift. That effect is 1, 2, 3, 4, 5, 6 orders of magnitude weaker than the base frequency at 400 megahertz. And so back when we were talking about magnetic nuclei, I said all protons are the same as all protons on our magnet. They will change their spin states at 400 megahertz plus or minus a little bit. This now is exactly the little bit. It is an effect 1,000,000 times weaker than the influence of the magnetogyric ratio and the big magnetic field. It's a bit of a miracle we can measure it at all, but thankfully we can, and that's what gives us the various chemical shifts we measure and rely upon to tell us about our samples when we do proton NMR spectra. And now we're going to do the same analysis, the same consideration, not for proton, but for carbon spectra. Now, carbon spectra have a considerably wider range on the PPM scale, we normally see 0 to around 220 ppm, much wider than proton. Now, remember, on our instrument, the carbon frequency is about 100 megahertz, which means 1 ppm equals 100 hertz for carbon on our instrument. But that does mean that we have a range of 220 ppm, 1 ppm, 100 hertz of 22,000 hertz from left to right, much wider than the 4,800 hertz of proton. This translates into a couple of interesting effects. One of them is that while we have seen plenty of examples of signals overlapping in proton spectra, where that one area around 2 to 2.5 ppm, where lots and lots of things tend to clump up, carbon spectra does not suffer from signal overlap nearly as much as proton spectra do, partly because there are just simply many more hertz, many more differences in frequency to look for. So where signals may be right over the top of each other in a proton spectrum, in a carbon spectrum, if you're lucky, they may be very close to each other, but still separated, still able to tell the difference between the two.